Thanks a lot, Heike, for introducing. So, ladies and gentlemen, it's a pleasure now to have a first talk here in this hybrid system session. We are dealing with this topic of hybrid system, even looking at the German context. We do not have so much hybrid system actually. So we have been working on hybrid systems since decades. So early looking at rural electrification and working in projects with Africa. And we also had about 20 years ago first purely inverter formed island grids without any diesel genset and so on. So that was part of our European activity with Greece. Kisnos is maybe a kind of well-referenced island grid that was formed purely by inverters, and we developed a kind of a technology and algorithms for that. So this is kind of a topic we are working on since decades on that, as I said, even not relevant on the German context. And it's now gaining interest because we are having the more and more higher penetration of renewable energies in the system, and so assuming we get a blackout in the future, we are very happy that since many years there hasn't been any major blackout incident, but if it appears, I personally find it extremely unsatisfying. If even the wind is blowing, the sun is shining, none of the citizens would have power anymore. And so distribution system operators are gaining this interest in becoming more responsible also for that. At present, the responsibility to restore the grid after a blackout is, of course, completely under the responsibility of the transmission system operator. As more and more generation is allocated in the distribution system, the distribution system operator is more and more also included in this responsibility and has to take part in that. And so we are running at the moment a very large German project with all TSOs, with a number of DSOs, manufacturer training centers, and so on, where we consider in many diverse case studies this topic of how to re-energize distribution system areas in that domain. So next to my talk is mainly concentrated on the low voltage grid, gaining some basic insights in that. And the second presentation actually is from Dario Laferte, who is also working in this project. It's called Netzkraft, and he's proceeding on that, going to the medium voltage grid actually, and to another case study that we are elaborating there. So having told a bit about this story, I actually go into my presentation. So I do it in substituting my PhD, Dirk Fetzer, who is actually working on that, doing his PhD in that domain. And I represent his results today. And I'd like to give a short outline on so we first will have a look into some modeling and simulation aspects, and then I will show some results. So first, we normally don't have really diesel gensets in the German context anymore, as we have a very reliable grid. So diesel gensets are more for emergency units at customer sites, but also grid operators use diesel gensets in case they have to maintain or repair anything in the low voltage areas, so they reconnect from the medium voltage, low voltage transformer, apply the emergency genset, and just operate further on, even being under a maintenance situation. It could also be imagined that, or not, it's not imagined, but during outages, diesel gensets are also allocated to critical infrastructure. This is mainly, for example, substations to get power in order for network restoration. So they are applied there. And of course, we see, I know in the Indian context, there's a huge number of diesel gensets as well. So I think this is a topic of high relevance here as well. So the same is with the industrial low voltage grids. Also there, we see diesel gensets and PV systems are normally used here for fuel saving. And so basically, there is a kind of a correlation given here. And so what we analyze is here some basic analysis. So what happens if I have a low voltage grid with a lot of photovoltaic systems there, small scale photovoltaic systems. And if I do not have any communication, so we are not in the smart grid session anymore that we have been just before the lunch, but it's now without communication. And so we are using a PV module. And so the grid codes, how PV systems in low voltage grids should behave, has been changed. So there have been modifications, and you can see that those modifications are quite relevant also for this network restoration stage. So we look at reconnection of old or new installed PV plants with regard to the difference in the grid codes. So what we do is considering a state diagram. So depending on the state, we have state changes. So you can see we are in, if we are in normal operation, then what happens for the PV system if it's in over frequency, so larger than 50.2 Hertz, then it's going to dynamically reduce active power. And in case that the frequency is out of the band, then it's going to be disconnected. Then if it's within a certain bandwidth, it can be reconnected in case it was disconnected. And so you see you can jump between the different states. So here you see the dynamic reduction of active power depending on the frequency. So this is quite important. So you see the difference if we look at the old systems. So the old system looks quite much more easier to be modeled in the state diagram, which means that in case that we have a defined cutoff frequency, the system is just disconnected. So that was, maybe you can remember the 2 days ago we had already discussed in the panel, in the plenary, about the 50.2 Hertz problem. So it was a time when hundreds of thousands of PV plants have had disconnection, frequency, over frequency protection at 50.2 Hertz, and within 200 milliseconds, many gigawatts could have been disconnected. And during the retrofitting, there was one category of hundreds of thousands of plants that were not able to imply this dynamic reduction. So what was done is that according to the distribution of different inverter models, so not simulation models, but type models, they were given a cutoff frequency of a given value, and according to the stochastical distribution of different cutoff frequency, aggregated wise, they would follow kind of this dynamic active power reduction. However, if you are in only one low voltage system and you are not in all of the 500,000 low voltage systems of Germany, there could be the situation where you have only inverters of a certain cutoff frequency because the location was not the most important one in the retrofitting action. So we assume here that in case that there is an old system, it has a fixed cutoff frequency. We also simulated a diesel genset according to literature values and a certain validation of the control signals. And so the idea is here, that we have the frequency as a control signal. So this is often done without communication, that the frequency is used as an information about the active power balance in the system. So if the 250 kilowatt unit is going below 80 kilowatt, which is kind of the minimal operational limit, then it's going to increase frequency in order to give the PV plants the information that maybe they should better reduce their active power feed in order to be able to leave the grid forming unit, the diesel genset here, under operation and not go in underloading situation. So this is done, so you can parameterize depending on your situation. So what we see is that we first assume the low voltage network is not supplied with power from the medium voltage. Then an emergency diesel genset is connected to the low voltage bus bar. The diesel genset is started and forms an island grid, and then the diesel genset is initially operated at 50.1 Hertz. That's an isochronous control mode that allows to sustain the cold load pickup phenomena. And if you have, if you might remember my values I said before, so at 50.1 Hertz, the PV systems will not connect because they will only connect. I can just show that here again. They will reconnect if the frequency is below 50.05 Hertz. So that means the PV systems are defined by this isochronous high overfrequency mode that they are not active. But then, of course, the frequency control mode, after having done with the cold load phenomena, so that at first it's higher load, then if this has been stabilized, then the frequency control is switched to the frequency depending, so the active power depending frequency control, and so then we start with the investigation. So looking there at the results, we can see that we see here over time. So we have 400 seconds that are simulated, and we see that here we connect the new PV systems. PV is now here in the number of 300 kilowatt, low 200 kilowatt. So this is a quite penetrated grid with PV. So this is analyzed here, and we see that the diesel genset has here in red, it's the frequency, it's at 50 Hertz. Then slowly the PV is going to increase because it's having a ramp up of increasing power when having connected. It's not just jumping to the nominal value, but it's increasing. And so it's increasing until reaching a certain value, and if a certain power is reached, then the frequency goes up because the active power of the diesel genset is going to underload constellation, and then the power of the PV power is actually freezed at a lower value. So see, it's not 300 kilowatt, but it's here around 130 kilowatt, according to the frequency signal. So the frequency now is a signal that defines the sharing of the load between the diesel genset and the PV power, realizing that not too much PV is feeding in, and that the diesel genset is not in underload operation. So this is working quite fine. So if you now see the reconnection of an old PV system, so assuming a 50.6 Hertz cutoff frequency, we see that the increase is much steeper. So the ramping was also not so defined in the older standard. And what we can see that there is a short increase of frequency, and diesel genset is regulated down, so it's taking over. So PV is taking over part of the loading from the diesel genset, and according that PV is just a small number here compared to load, we are still under nominal frequency constellation. However, if we increase the share of PV compared to the load, so it's now equivalent, we can see that it's coming into fluctuation. Yeah? So that means the PV system reconnects. Then we have a steep decrease of the power and of the diesel genset. Thereby the frequency increases. As the frequency increases at 50.6 Hertz, we have a disconnection again, and so is oscillating. So you see, with the old grid code we have had in Germany, we wouldn't be able, under high penetration situations, to restart the system towards a stable condition, which means that that the result of the new grid code is much better, allowing us a good situation. So we tested that also in a real grid with 150 households and 21 PV systems, and we were doing similar studies. We were looking at a mix of both. So we have considered here 8 old and 12 new PV systems installed. We see that it's going quite smooth. So we have here a rapid connection of the old PV systems, a smooth connection of the new ones. We also see that the frequency increases here, and this is causing a limitation then for the new PV systems. And finally, we have a stable load sharing. So that is working quite fine. But as well, if we have a huge number of old PV systems and we have only few new PV systems, then we see that we come again into this oscillation mode. So this is, I'd like to clearly, in this simple example, give you a clear message that the grid code definition is very important, and design it early enough in a way that you can use PV systems in all the different grid conditions in a stabilizing way and not destabilizing way. So finally, some conclusions on that. So the reconnection of new PV of PV system, not new PV system, but the PV systems according to the new grid code works very fine, because the power is freezed and the frequency droop that is applied to the diesel genset as well as to the PV system causes a stable island operation. So this is very important. But in Germany, we have to deal with old systems that have a fixed cutoff frequency, which can cause instability situations. So they will be overdone if there are no new PV systems installed and so on. And in the future, this will not be an issue anymore. I hope you will not do the same mistake as we did in dealing with that. Well, what has been analyzed here as a general rule of thumb is that the available PV capacity of old PV systems should be, of course, then smaller than the load of the system plus the losses and minus the minimum diesel power. And so I think this is quite logical that it's in that way. And this is a little rule of thumb, hopefully not necessary to be applied here in Indian or other contexts. So I will finalize with my presentation and also pave the way to the second presentation of Dario Laferte, who is then working on top of that, going into the medium voltage grid. So after having installed, after having resupplied the low voltage system, so to rebuild the system again. So thanks a lot for listening, and I hope we can have some questions now, because regrettably I have to leave after the next presentation, having another presentation in the other session, and so I have to excuse myself, and hopefully we can have the discussion now. Thank you.